obtained as a linear combination of the original guys. So the recording just started. Okay, so I'll just repeat. So last class, we obtained the Fock operator equation, which was in a which was not in an eigenvalue form, which made it difficult to solve. So we proposed that we change the set chi A to a set chi A prime, such that the operator equation becomes an eigenvalue equation. And to do that, we said, let us have every spin orbital as a linear combination of the old spin orbitals, so the original spin orbitals, and the transformation matrix is then UBA. In particular, we said this transformation matrix should be unitary because unitary matrices would keep the spin orbitals orthonormal. And the mu determinant that would be formed from the chi A primes, that would be related to the old determinant psi naught by a phase factor, which means that all expectation values would remain unchanged, because the bra function will have a e to the power minus I phi and the ket will have a e to the power I phi, and those would cancel in all cases. And these would be equal to psi 0 naught psi 0. And if A is the Hamiltonian, it also tells us that the energy is also unchanged. And e to the power I, and we had shown in an earlier class that determinant of U is actually e to the power I phi. So you can refer back to the older class to see this. Now, so what has happened? So the equation that we have now obtained, that is called the canonical Hartrip equation. Now this first equation, this could have had many solutions. But when we add the additional condition that I want my Fock matrix to be diagonal, then we are sort of honing in on one particular solution. So this solution, the set chi A prime, that satisfies the variational equation, and it also satisfies diagonality of F. So an additional condition has been imposed to make the equation more easily solvable. Okay. But this energy that we obtain from this is, of course, an energy that would be obtained from any set of chi A that would have solved the original equation if we could have solved it directly. Then all these solutions would have the same energy and the same expectation values. So we are not losing anything. We are just finding the easiest and most convenient solution. Okay. And in doing this easy solution, what happens is every chi A prime becomes associated with a particular energy, epsilon A, which we call the orbital energy. And this also helps us in physical interpretation, like we have done before. We have seen that the energy of occupied orbitals are basically the ionization potential of the electron placed in that orbital, and the energies of vacant orbitals or virtual orbitals are the electron affinities of those orbitals. So if you were to place an electron in that orbital, it would either require that much energy or release that much energy. Okay, and from the point of view of this, there is exercise 3.5, okay, and we will work this out so that you can do other examples of this kind as well. So so exercise 3.5 from Zabo Ostrund, it says that show that if you have an n minus 2 electron determinant where the electrons have been removed from chi c and chi d, which are two particular spin orbitals, then the energy required will be ECD equal to negative of the orbital energy of C and negative orbital energy of D plus the interaction of CD. So intuitively, this would be the case. If you want to remove an electron just from C, then the IP would have been minus epsilon C. If you had removed it just from D, then epsilon D. But if you remove both, then you also lose the interaction between the two. But let's see how we will work it out explicitly. So let's denote the two determinants as n psi. This is the original determinant, and then you have n minus 2 psi CD. So this is notation for the fact that two electrons have been removed, one from C and one from D. Okay, and ECD is the energy required to remove the two electrons. So that is the energy of the final state then. Minus the energy of the original state. Simple enough. Now, in order to obtain this expression, the assumption is that the orbitals have not been re-optimized for the n-2 state. So, assuming no re-optimization of orbitals for the n-2 state. Now, if you had optimized the orbitals for the n-2 state, the representation of the n-2 psi CD determinant would be in an entirely different basis, and no simple expression would have been obtained. So even when the question does not mention that they're assuming this, the fact that they want you to show that the energy is a simple expression indicates that you cannot, that you have not optimized them. Okay, so it's an underlying assumption. And now let us just write the energy expressions, which is simple enough to do. Let me just write then En. I think that is easier. En is equal to sum over A not equal to C and D. So I've written the sum up to n, but have said that A is not equal to C and D. So effectively the sum is up to for n-2 orbitals. A plus half sum AB, and here again neither A nor B can be C or D. then n minus 2e CD. Oh, sorry, this is n minus 2 CD. And then now I just write NE. And this is sum from 1 to n, AHA plus half sum AB, AB. And ECD is then n minus 2 ECD minus NE. So let's just directly write the difference terms. So I'm subtracting equation 2 from 1, but 2 has more terms than 1. So I'm just writing the terms which are extra in 2 with a negative sign. So from the 1 electron part, you will directly get minus CHC minus DHD. Now, more careful consideration is required for the 2 electron part. So the terms which are there in 2 but not in 1, they are minus. So when A is C, so that's CB, CB. Then you have when B is C, so that is AC, AC. Then you have when A is D, and then when B is D. And then when A is C and B is D, so that's CD, CD. And when A is D and B is C, that's DC, DC. Now see, for every line, so CB, CB, and okay, and there are sums here, of course. So there is a sum over B here, a sum over A here, a sum over B here, a sum over A here, a sum over, no sum here. Okay. So look at the index for the sum. So the sum is a dummy index. So this and this are basically the same term, because I can let's say in the second term I can write A sum over A as sum over B, and then by particle symmetry I would get CB, CB. Okay. Here also, if I replace A with B and then use particle symmetry, I would get DB, DB. Similarly, this is also CD, CD. So the halves will go away and I will have minus CHC minus DHD and minus sum B, CB, CB, and then minus sum B, DB, DB, and minus CD, CD. Okay. Then, if we club together CHC and CB, that is the Fock operator expectation value with respect to C. And we can club together DHD and DB. So I get minus CFC, then minus DFD, and minus CD. And the expectation value of the Fock operator is the orbital energy. So I get minus epsilon C minus epsilon D minus CD, CD. And that is what was asked in the question. So the language for my question can be different from that in Zabo, but basically it's what they wanted. Okay. I just wrote it from memory, so it's not exactly the same. So you just need to figure out what terms are different between the two energy expressions. Write the two energy expressions and see. So you can try yourself exercise 3.6, which is even shorter than 3.5, where you have to show that the energy difference between an n electron determinant and an n plus 1 electron determinant, where the electron has been added in orbital r, is equal to minus of epsilon r. I think basically this is what they want you to show. So minus epsilon r means you have to show RHR minus sum B, RB, RB. So I'll give you 5 minutes and you can maybe try it out. And once you're done, let me know. Whoever finishes, let me know.
I'm done.
Done? Okay. Let's wait 2 or 3 minutes for the others. Anyone confused about anything? You should, I don't think you should be, but if you are, please ask.
I did it.
Okay. Good. So you just need to write the two energy expressions and then use some symmetries and you will be done. No problem. I will also quickly write the steps in case someone is not sure. So I have also worked it out for anyone who is stuck anywhere in between. So we go back to where we were in the Hartrip recap. So the next thing that was required was going from the spin orbital basis to the spatial orbital basis, because we cannot explicitly handle spin coordinates numerically. So this is something we have to do. So the next step in Hartrip is to go from spin orbitals to spatial orbitals. And the derivation that we have done before, and also the one I'm recapping now, is the restricted closed shell Hartrip. We will talk about the unrestricted, but after the test. Okay. And what does the restricted closed shell Hartrip mean? It means that in the determinant made up of all the spin orbitals, we write each spin orbital as a product of spatial and spin parts. So if the spatial part is psi, then if the spin part is alpha, you just write it as psi1. And if the spatial part is psi1 and the spin part is beta, you put a bar. Probably comfortable with this notation after all the assignments. So this is a way of representing the determinant. And then the expressions we have derived in the class before, so you can go back and check. So the energy expression for this determinant in terms of only spatial orbital integrals, where we have integrated out the spin, is the sum over all the spatial orbitals, which are half in number because it is a closed shell system. So number of alpha equal to number of beta, and in for every orbital, the spatial part is the same for the alpha and beta spin. So that is what is meant by restricted. And when you integrate out the spin, you get a factor of 2 over here in the 1 electron part, and in the 2 electron part, is there a half here? I forgot. No, I don't think so. It becomes a 2 JAB minus KAB in the energy of the determinant, where A and B are spatial orbitals. So the Coulomb part gets doubled and the exchange part it no longer has the same factor as the Coulomb part. This is the energy of the full determinant, and each orbital energy that also changes, but there the 1 electron part is the same, and the 2 electron part of the energy that again develops a factor of 2 in the Coulomb integral, and the exchange has the same minus 1 factor. The equation, on the other hand, in spatial coordinates now, that looks exactly the same. And now that we have represented our equation in terms of spatial orbitals, we can expand the spatial orbitals in terms of a basis. So the next step is now introducing a basis. And every psi I spatial orbital is then written as a linear combination of k basis functions. And the coefficients of these basis functions now become the unknowns. So earlier it was a bit abstract because you had to find out functions. Okay. But finding out a function out of the blue is not easy. So every time you need to find a function, people would normally have a basis and you find out the coefficients of that basis. And the coefficients are just numbers. So those can be obtained by algebraic equations. The only type of solutions where you get functions as output are when you solve differential equations. And we don't want that. We want to do things numerically in terms of algebraic equations. And then using a basis is what people have found to be the best way of handling this. And the number of basis functions is again in our hand. So let's say we have k basis functions to represent each orbital, and k is not necessarily equal to n. And this is a very crucial fact in Hartrip, that k is not necessarily equal to n. But k must at least be n. Let's see why. So if I have k basis functions and I use this expansion in my Hartrip equation, then my Hartrip equation becomes f mu nu c nu I equal to epsilon I. This is still the same energy of the molecular orbital. So I is the molecular orbital index. And mu and nu are the basis function indices. C nu I. So the equation becomes of this form, and since my mu and nu are of dimensions k, so this is k by k, and nu is also k, and again here you have k by k, and nu is again k. The number of solutions that you get are also k, because we convert this to an eigenvalue equation, and there all the matrices are square matrices. So your coefficient matrix that you obtain by diagonalization will also be k by k if the matrix that you're diagonalizing is k by k. So I also ends up ranging from 1 to k. So this tells me something, that the so it places some, so I can places some constraints on what k can be. So k minimum must be n. And why is that? Because I need at least n orbitals to represent an n electron system as a determinant. So the minimum number of basis functions that I need is n. However, there is no constraint on k being greater than n. But when k is greater than n, then the number of solutions that I get are also more than n. And then many of these solution orbitals will not be in my ground state determinant that I make. So they will not be a part of psi 0. But what are they? They are then called, so all the psi I for I greater than n, they are called virtual orbitals. So they are the empty orbitals. So we had already introduced them when we spoke of electron affinity and putting electrons in the empty orbitals. But why we get empty orbitals is because of the introduction of a basis which is larger than the number of electrons in the system, or the number of orbitals, occupied orbitals in the system. And the remaining solutions that we get, they are called virtual orbitals. And the physical significance is that that the energy of these orbitals are the electron affinities of the system. And for post-Hartrip methods, they also help us in improving our psi naught and introducing electron correlation, which we will also discuss later on. Okay. And the quantities in the equation, just for completeness, let me just write them down. So So S mu nu is the overlap of the basis functions, and this is not delta mu nu. And F mu nu is the elements of the Fock operator in the basis. Okay. Now the explicit expression for F mu nu is still not evident to us at this stage. Okay. But we will, of course, do it soon enough in just a minute. Before that, just let me write this equation in a matrix form. So this is simply Fc is equal to Sc epsilon. Now, because I'm writing it in matrix form, I am ensuring that my dimensions match, or the index pairings match. So I have a I at the end here, so I have shifted epsilon. That's just to make sure that you don't make mistakes when doing your matrix algebra. In this case, of course, all are square matrices, so you don't have a problem. But if you didn't, then it would be a problem. Okay. Now let us talk about the expression for F mu nu. So we have said that F mu nu is the expectation or the matrix element of the Fock operator between two basis functions. And the Fock operator has a 1 electron part and there is a 2 electron part. And remember, now this is spatial orbital. So now you have to use the expression of the Fock operator in spatial orbital. This integral is called H mu nu core. And here A is a molecular orbital index. So that means that you have to somehow remove it before you can evaluate things simply knowing the basis. So you don't know the molecular orbitals before you have solved the equation. But solving the equation involves computing F mu nu. So I cannot leave the A's here. I have to again introduce the basis set expansion for the MO. Someone wants to say something? No? Okay, so I'm introducing a basis set expansion of the molecular orbital A. Okay, one for the start part, so for the mu A, for the A's in the bra part of the integral, and another for the A's in the ket part of the integral. So this is for the ket part, which means that I need another summation here. So I need another summation on the ket part and a sum on the bra part, which is on sigma. Okay. Then I have okay, and I'm also taking the 2 common because I have something more in mind. So mu sigma nu lambda minus half then mu sigma lambda nu. So we have done this before, but I just wanted to highlight some points. So this is this. Now there is a sum on A, and the A is restricted to the coefficients. So we carry out this sum on A along with the factor 2, and we call it P lambda sigma. And we have the remaining integrals here, mu sigma nu lambda minus half mu sigma lambda nu. Okay. So now we have an expression which depends entirely on the basis set indices, mu nu lambda sigma, and the MOs have been hidden inside this quantity, which is called the charge density matrix or the just density matrix. Okay. And another compact notation is used, which I will write here for is that this is called G mu nu. So this is called the 1 electron part, and this is called the 2 electron part of the Fock operator. And we also see that instead of having the Fock operator as a function of or directly of the coefficients, we can also write it as a function of the density matrices. And the equation that we have is then Fc equal to Sce, which we still need to solve. Got it? But now, even after introduction of the basis, this still so this is now a matrix equation. So this is something we can solve in principle, but this is again not an eigenvalue equation, so it cannot be directly solved yet. Okay. So this is still not an eigenvalue equation. So we have encountered this problem before, and we encountered it again, and we will do a similar trick to get it to a eigenvalue equation. So we want to convert this to something that looks like an eigenvalue equation. And for doing that, now we say that the new coefficients are a linear combination of the old coefficients. We have just done the reverse. So we've written it in the reverse order. So before when we changed the spin orbital basis, we said that chi a prime is a linear combination of chi a. So the new things were a linear combination of the old things. Here we have put an inverse, which means that we are writing the original coefficients as a linear combination of the new coefficients. So we will see how that helps us. So putting c equal to xc prime in our equation, in the original equation, we have f xc prime equal to s xc prime epsilon. Then we multiply both sides by x dagger. Okay. We call this as f prime c prime. We have x dagger as x c prime epsilon. And we require, or we require that x is determined by the condition x dagger sx equal to I. And if that is the case, then f prime c prime is equal to I c prime epsilon. And this is now an equation that can be directly solved. Okay. Now the next question is, of course, what is x? So does this condition completely and uniquely determine x? Well, it does determine x, but it is not uniquely determined. We have various options. We can have x equal to s to the power minus half. Then you would have s to the power minus half s to the power minus half. That is certainly I. Okay. And you can also have x equal to u, which is where u dagger su is equal to s. So basically u is then the diagonalizing matrix of s. So this is the diagonalizing matrix of s.
Hello, hello, ma'am.
Yeah, sure. Tell me.
Madam, can you tell me in summary what we are doing?
So this is actually across the two classes. I am trying to give you a summary of the Hartrip method. It has many steps. So that is the problem. So this last step, what we're trying to do is we're trying to get a matrix equation in eigenvalue form, which will tell me the coefficients of my
Madam,
molecular orbitals.
oh, madam, actually the Hartrip single this is not diagonalized. So here I just diagonalize the matrix in the.
Here, we are trying to get it in some form where you can directly diagonalize. But for Hartrip, you will need an iterative procedure because the Fock matrix contains the coefficients or the density matrix. But if you left it at Fc equal to SCE, you can't even do one step. So you're stuck. So the problem here is that even in Fc equal to SCE, or even here, the unknown, you have two sets of unknowns. You have the coefficients and you have the energies. And the only form of equation we know where we get both these things together is if it is in eigenvalue form. So that is why we want to get the equation to an eigenvalue form.
Here the coefficient and energy are both are unknown.
Both are unknown, yeah. That is the problem.
Oh.
So the only way we can do it is by getting it to an eigenvalue form.
Okay.
And we're trying to do this at multiple steps. And there are many little tricky issues. That's why it seems a bit complicated. That's why I'm repeating the full procedure so that you remember the steps and why what is done. That is the important thing to know. Why you do which step. Okay. So here, this step that I just spoke about, I had Fc equal to SCE once I put in a basis. And this again, C is unknown, E is unknown, I cannot solve it. So now this also I have to get to a eigenvalue form. How do I do it? I introduce again a transformation of the coefficients to get to a diagonal form. But that also transforms my Fock matrix. So I have to write F prime. Okay. And after introducing x, I find x such that my s goes away. Because the s was the problematic term in the equation. So I find x such that s goes away. And with this x, I transform my Fock matrix.
Oh, okay, ma'am.
Yeah. But now we are again faced with choices. So x dagger sx equal to I does not uniquely tell me what x is. I can make many choices. Like the two most common choices, what I was talking about right now is s to the power minus half is one. that will also satisfy x dagger Sx equal to I. But if you take x equal to u s to the power minus half, so the small s is the eigenvalues of capital S and u is the diagonalizing matrix of capital S. So even if you define x equal to u s to the power minus half, you will also satisfy x dagger Sx equal to I. So let's see what happens. So x dagger is then s to the power minus half u dagger, and you have s, and then x is u small s to the power minus half. Okay, s to the power minus half. U dagger su is small s. Okay, so this is also I. So both the choices satisfy the condition that we need. So now we have to decide which one is better. So basically, both are equally good from the point of view of maths, but going through the diagonalization allows us to do something more. It allows us to check the eigenvalues of capital S for linear dependence in the basis. So if you have very small eigenvalues of S, then it means that you have linearly dependent basis functions. And you should, in principle, remove them. Okay. So if you go through the second method, which is called the canonical orthogonalization. Okay. And the first one is called symmetric orthogonalization. So if you do the second one, because you diagonalize S, you can have a look at the eigenvalues of S. And if you have small, very small, close to zero eigenvalues, you can remove those eigenvalues and remove those rows and columns from the X matrix also. Okay, and convert the X matrix from a square matrix to a rectangular matrix. And when you transform the Fock matrix now with these rectangular X matrices, you will get a Fock matrix in a linearly independent basis. And that will make your equation numerically stable. Okay, so that is why the second method, so canonical orthogonalization, is preferred because of this added benefit. So I'll write it down now. Let me write it properly. So going through the diagonalization of S allows us to check for linear dependence in our basis set. Okay. If some entries in small s, which is the eigenvalue matrix of capital S, are close to 0, we can remove them and the corresponding entries in X. Okay. Then this X will tell me the transformation from my linearly dependent basis to a linearly independent basis, and we can apply this X to F and C. And when you do that, then F prime and C prime then become matrices in a linearly independent basis. So did you get the point? Therefore, canonical orthogonalization is preferred over symmetric. Okay. They're basically very close, the two methods. But yeah. But this helps us. Okay. So you got my point. And in one more class before, we had discussed why simply explicitly finding the linearly independent basis functions is very expensive numerically, and going through X is cheaper. So you can go back to that video and check if you like. We are out of time today. So I hope Hartrip is clear to you. We will not come back to the derivation of Hartrip equations again. We will talk about basis sets on Monday. And then let's see what we do. And next Saturday, 4 to 5 p.m. is your quiz on the Hartrip theory. Okay, thank you.
Hello, ma'am.
Yeah.
Tomorrow, ma'am. The quiz.
No. Next Saturday. Next.
Oh,
Saturday.
next Saturday. Oh, okay then.
Okay. Fine. Bye.